background. There we go. Of course, wouldn't be a talk about ice shelf stability if I didn't at least mention Larsen B once, or more likely several times. So this is MODIS imagery of the Larsen B just before its sudden collapse in 2002. And we can see that within just a few weeks, there was sudden and dramatic collapse right across the ice shelf, with an area about the size of Rhode Island being lost. And now I live in the US, I can appreciate that that is a very large area of ice. I had no idea how big Rhode Island was before I moved here. I had to always convert it into units of Greater London or something for the Brits to appreciate. But anyway, I'm sure most of you are aware, lots of ice lost very, very quickly. So the reason that we care about ice shelf sudden collapse is because the ice shelves, just to give you the quick ice shelf 101 in case we have people here who don't have a glaciology background, Antarctica is land, it's covered by ice, and that ice flows off of the land and floats on the ocean, and it's these big floating areas that we call ice shelves, and these really are large features. Some of them are up to the size of France, for example, so huge areas of floating ice. And why they matter, especially in terms of the context of global sea level, is that they provide resistive stresses that keeps a lot of that ice that's on Antarctica that's trying to flow off of the continent on the continent. So it kind of regulates the flow off of the ice shelf. Icebergs will carve from the edge of the ice shelf and add ice to the ocean, well, remove that floating ice anyway to the ocean. And snow will fall on Antarctica, and so on, kind of keeping things, what's the word I'm looking for? But anyway, there's a balance if we kind of lose ice from the ice shelf and gain snow on Antarctica. But if that ice shelf suddenly collapsed, such as in the way that Larsen B did, then those resistive stresses are lost. That ice that is on Antarctica is then free to speed up and float into the ocean. And this will, of course, contribute to global sea level, because that ice shelf, while it's floating on the ocean, by Archimedes' principle, it doesn't contribute to sea level, but anything that goes from off of the land and into the ocean will contribute to sea level. And this was noticed in the case of Larsen B. The glaciers that previously fed onto that ice shelf were observed to accelerate after the ice shelf's collapse. So in terms of Antarctica's contribution to global sea level, at the moment, it's actually contributing less than Greenland, which is a much smaller area of ice, but we do know that it is accelerating. So one of the questions that motivates my research is how much is that going to accelerate by, and how much is that going to contribute to sea level in the future? And in order to really answer this question, we need to know what's going to happen to the ice shelves around Antarctica. If we lose those ice shelves, are we going to get accelerated sea level rise? And is Antarctica going to play a bigger role in global sea level in the future? Now, to know about the stability of ice shelves and to try and predict how they're going to change, one thing that we really need to think about is, sorry, I've managed to get these slides out of order somehow, is the surface of the ice shelves. So ice shelves can become unstable essentially in two ways. So one of those ways is that they can melt from their underneath. So as the ocean warms and it causes melting underneath the ice shelf, this can cause thinning of the ice shelf. And this is a very key process in their stability. But the processes that I care about happen on the opposite side of the ice shelf, where the ice shelf is influenced by the atmosphere. And this is something that we think is very key in the sudden collapse of Larsen B. So we can see here in that same satellite imagery of Larsen B that I showed you earlier, just after the collapse. If we zoom in, see if I can get the pointer here. There we go, yeah. So down in the bottom corner here in this red box, we can see these kind of black features that were on the ice shelf surface. And these are lakes that were observed on Larsen B's surface. And these lakes were noticed to drain just before the ice shelf collapsed in a chain reaction. So you get one lake draining and those around it and those around that in this chain reaction that we think might have been key in causing the ice shelf to become suddenly unstable. Now, there's a few different theories about the way that surface meltwater can influence ice shelf stability. So there's this chain reaction idea. There's also the idea of water getting into crevasses and the pressure of water causing these crevasses to expand, and that leading to ice shelf instability as well. But it's definitely quite clear that these lakes are playing a role in ice shelf stability, and knowing more about those is really important if we want to know how the ice shelves are going to behave and evolve in the future. Okay, so, So I am actually a mathematician by training. So the way that I think about ice shelves is more like this. So no more satellite imageries. We're now thinking about a model ice shelf. So we have the ice on top of the ocean, and then snow and Foehn sitting on top of that. And if you're not aware, Foehn is essentially a word for old snow. So snow that's kind of been there for several years and has compacted and is getting dense, but is not actually ice yet. And one key point to notice here is this line here is the pore closure depth. And that's where the snow and the Foehn has compacted enough that it's now dense enough that any air bubbles in it, any pores in it are closed off. So it's not completely become solid ice, it still is kind of like very bubbly, but it is impermeable to any meltwater that may reach this depth on the ice shelf. So that's what's key here. Any melting at the surface that happens can't get any lower than the pore closure depth. So this is the area of the ice shelf that I really need to think about, is where the water can actually get into the ice shelf. So there are three different ways that these lakes could essentially be forming on ice shelves. So we have a schematic here. This area is snow, below this is ice, and the pore closure depth is this line here. So water can't get any deeper than that. So the most simple situation is that we get some melting at the surface of the ice shelf. So the surface will lower a bit. That water will percolate down into the ice shelf. It may get as far as the pore closure depth. And eventually when it reaches the pore closure depth, there's nowhere for the water left to go. So it will just sit in place and saturate the snow from the pore closure depth upwards until eventually there's nowhere at all for the water to go, and it will form a lake on the surface of the ice shelf. Now, this is possible in situations where there is relatively little snow or Foehn on the ice shelf, but actually if you have several or even tens of meters of Foehn, which is the case on some ice shelves, this is a pretty unlikely way that lakes are going to get formed, because that is going to take a real lot of water to have to be produced in one area on the ice shelf. So a more likely situation is that we get some melting in some areas, and maybe that will get down through the ice shelf and it might reach the pore closure depth, but there won't be enough to saturate the snow. But because ice shelves, of course, are not completely flat, we also get some lateral transport of meltwater, meaning that water can move across the ice shelf surface, and lakes are able to form in some areas where that water starts to accumulate in topographical lows. Now, the final situation is that something I've not mentioned so far is that water won't just kind of go down into the snow and percolate as far as it can get, because the snow in Antarctica, unsurprisingly, is quite a lot colder than the air temperature sometimes. So even if things at the top of the ice shelf are warm enough, you've got melting, that water doesn't have to get too far before it reaches a temperature of the snow that is below freezing. So water will refreeze within the snow. So if we get enough water that refreezes within the snow at a certain level in the ice shelf, then we will get solid lenses of ice forming. So this means that any future melting actually doesn't have to go down as far as the pore closure depth, because it's blocked by these refrozen lenses of ice within the ice shelf. And this means that actually the snow, the remaining snow above the ice lens, can saturate much more quickly, meaning that a lake is able to form much faster if these ice lenses do occur. Now, in order to investigate which of these three processes happen, I developed a one-dimensional model for surface melt on ice shelves. So this is a 1D vertical column looking from the surface of the ice shelf downwards. It's currently set to run through the top 35 meters because the particular ice shelf, Larsen C, which I'll come to in a second, I was interested in has a very thick Foehn layer, but obviously any of these things can be adjusted for different ice shelves. And it's run over a 5 centimetre spatial resolution and an hour temporal resolution. But all these things are flexible. Only the initial density, temperature profiles, and any automatic weather station or reanalysis forcing we use are dependent on the location. So any of these variables can be switched up depending on which ice shelf or even ice sheet you want to use this model to look at. So the way that the model works, our initial setup, so we have, this is the ice shelf surface, everything below that is snow and Foehn going down to ice. So first of all, we have the surface energy balance at the top of the ice shelf. So pretty much everything here is an input from weather station data, so all the kind of Fs here. Anything that's an F comes from automatic weather stations, and then that is used to calculate the surface temperature, or this capital T here, and the way that that changes over the surface boundary. We then use the heat equation to work out how quickly any temperature changes at the surface then penetrate down into the ice shelf. And finally, we just have a zero temperature gradient bottom boundary condition matching observations that we have. So this is fairly straightforward. It's just a heat equation with 2 boundary conditions, but when things start to get complicated is when things start to melt at the surface, because then we have to change these equations. So first of all, the surface energy balance at the top here gains this red term, this dH/dt, and that's to account for the change in height, because when snow melts at the top of the ice shelf, we lose some of the height of the ice shelf, and that melted snow then percolates down. And what happens to that melted snow is, as I mentioned before, it will reach areas that are colder than the surface, and it will likely refreeze within the snow. And that's what this extra yellow term here in the heat equation then accounts for. Because not only does this refreezing of the snow cause a density change and create these ice lenses, also the refreezing of this water releases latent heat. So it will actually act to heat up the snow around where it's refreezing. And we get a situation that we actually get an isothermal layer near the top of the ice shelf, where all this water is being produced at the top, going down into the snow, refreezing and raising the temperature of the ice shelf. So water can essentially only really reach the pore closure depth once we have an isothermal layer going from the top all the way down to the pore closure depth. So one particular case study that I was interested in looking at with this surface melt model was the Larsen C ice shelf. So that is Larsen B's next door neighbour. It's currently Antarctica's most northern ice shelf. And the reason it was so interesting to me is because if we just zoom in on this satellite image here, we can see there's pretty significant melting going on the ice shelf, just in select areas at the moment up near the Peninsula Mountains, but there's really very large amount of melting going on. So I wanted to know more about that melting and what does it potentially mean for the future of Larsen C. So when I initially ran this 1D column model, I discovered that, first of all, we did get melting on the surface of Larsen C, which is good because that's been observed. So that was nice that the model found that. But what we found was that water was getting down into the ice shelf, down to almost like over 20 meters of depth in the ice shelf, and it was refreezing. So we're getting some pretty solid layers of refrozen meltwater or kind of a slushy water ice mix within the ice shelf. But this never actually reached up to the surface. We never got completely saturated snow in the ice shelf. We can see here that the snow is getting saturated. So this here is showing you the water content of each layer of the ice shelf on the x-axis. And then, sorry, I should have mentioned before, depth, 0 is the surface of the ice shelf, and negative numbers are looking down into the ice shelf. So we can see that the ice shelf here is starting to get saturated with meltwater, but actually there isn't enough water to saturate the ice shelf all the way up to the surface and form a lake, which is obviously what we're trying to get the model to reproduce because they have been observed. So what is missing from the model that we needed to include? Well, first of all, the weather station data that I had available at the time of this study was not located in an area where the lakes have been observed. So actually it's kind of reassuring that the model wasn't making lakes because they shouldn't be where the weather station data is. It's kind of nice that actually there's a lot more Larsen C data out there these days. So that's great that we do have observations from near where these lakes are occurring. But when we don't have those observations, that meant that we were missing a very key process. So the lakes, as I mentioned, are located right up next to the peninsular mountains. And that means that this is an area that is very highly influenced by Foehn winds. So Foehn winds are essentially the warm, dry downslope winds that run across ice shelves. So they kind of come up over the peninsular mountains, and then when they come down the other side, because they are then, as a result of the latent heat release during their condensation as they go over the mountains, they then blow this big, warm, dry area over the Larsen C ice shelf. And that means that they are very key in melting because they're heating things up enough on the ice shelf that it seems that they were an essential process in these lakes forming. And there has been research done since that shows that even during the winter, there is lakes that can form on Larsen C that are correlated with these Foehn events. So these are really important and they needed to be included in the model. So we added in a Foehn wind effect in our data to match the observations we did have. Obviously now this can be done with the actual Foehn data, which is great. And the other problem is we're trying to use a 1D model to account for two-dimensional processes. So there's also the lateral transport of meltwater too. So the solution at the time to keep the model in one dimension, because that was key at that time, it was supposed to be something that was very quick and easy to use. And also I needed to graduate with my PhD, so there was not time to turn that into a larger model. But what we did at the time was that we multiplied the melt that was found in a certain area to try and account for the amount of melting we would have in a topographical low. So we'd estimate the catchment area of a lake and say, well, how much water do we think would actually be able to realistically get into our lake during the melting time period, and then add in that extra water at the top of our model. Now, obviously, this isn't ideal, and I'll come to why we can do better than that soon, but this was the solution for keeping the model in one dimension. And we're also able to check if the catchment areas we were thinking about were realistic. So this is some lakes on Larsen C taken from Landsat imagery. So just comparing the number of ice pixels to the number of lake pixels to check that we weren't doing anything too crazy and we were putting realistic amounts of water into our lakes. So when we did that, we found several things. So first of all, running the model with these extra components in gave us an isothermal temperature layer going from the top of the ice shelf at 0 down into 25 meters deep into the ice shelf. So we can see here we've got temperature running along the x-axis. Everything in the top 25 meters of the ice shelf is at 0 degrees, or the melting temperature. But more interestingly, when we looked at the density profile of those same model runs, so this was running the model over a warm year where we knew definitely that lakes had formed. If we zoom into what's going on down the bottom of the model, we can see these kind of spiky features in the density profiles. Now, those of you who are quite mathematical minded, I'm going to anticipate I'll get questions on this because it does kind of look a bit like a numerical instability. I know we worried about that at the time that this happened, but I did some pretty thorough testing into this, and it does turn out that this is not an instability, this is an actual feature that is occurring because these spikes in the density actually represent ice lenses that are forming within the snow. And so this made us think a lot more about how those lakes were forming. It suggested that those 3 different methods for lake formation that I showed you, it was the final one that is occurring. Those ice lenses were present and potentially meaning that lakes can form more quickly than if water was having to saturate the Foehn all the way down to the pore closure depth. And shortly after we did this study, a team from Swansea and Aberystwyth universities in the UK actually went out to Larsen Sea. And when I saw them after this, they showed me these images, which were particularly exciting because what they've done here is they've dug a snow pit into the ice shelf in an area where they thought that significant melting had happened during the melt season. So you can see here, this is about 2 meters deep. Then they dug an identical snow pit directly behind it. So we had two 2-meter snow pits and a wall of snow between those. Then by shining a light through that wall of snow, they could see this. So there are very clearly ice lenses forming within the snow, a very significant amount of ice lenses on Larsen Sea. So this is really nice that this field data backed up what the model was saying, because that's what we hope for as modelers, that we will actually model what's realistically happening and someone will be able to prove that for us. So that was really nice, and that gave me the confidence to then go on and continue to build on the model to actually look at the lakes themselves. Oh, sorry, that's just showing you that there is an ice lens there with that arrow. So the model set up with the lake looks more like this. So we have the same as before, same bottom boundary condition, same use of the heat equation in the Foehn. But then the surface energy balance changes because, of course, we no longer have melting at the surface. Any extra energy at the surface is going to go into heating up the lake. So that's what this term here, added to the surface energy balance, is going to give us. Then we also have this term here, which is the heat transport through the lake, and we say that the lakes do become convective almost as soon as they form. So research from ponds on sea ice suggests that they are well mixed from being about 10 centimetres deep, and these lakes on ice shelves are generally quite a lot. They can be several metres deep. So we think it's fairly safe to assume here that they are well mixed. And then at the bottom, this boundary here is held at the melting temperature because, of course, this is the transition from water into ice. But we also have this here is a Stefan condition, which accounts for the change in the boundary, because as the lake heats up, that will then continue to melt the snow below the lake and cause the lake to get deeper, because lakes, of course, have a much lower albedo than the surrounding ice shelf. So you're going to get more energy heating those up and causing them to expand vertically as well as they melt the water below them. And we also, as well as looking at the development of the lake, we also look at the refreezing of the lake too, so we can model the whole lake life cycle over consecutive years, because it's not thought that these lakes remain between melt seasons, at least on Larsen Sea. We think that they refreeze over totally between melt seasons. So again, same model equations that I've just shown you, but in addition to this, we have here another Stefan condition, which now models the expansion of this ice water boundary, so the freezing of the lake from top to bottom. And also, again, a altered version of the surface energy balance here. So that's back to the original surface energy balance, obviously without a melting term, because it seems like once the lakes refreeze, we don't really get any more melting on the surface. So this model allowed me to look at the lake's life cycle over multiple years. So this plot is kind of a bit weird to think about, first of all, because we're looking at a 1D lake, so I'll just try and run you through this. But this is essentially taking a year of data on Larsen Sea that we knew was particularly warm and there were deep lakes forming, then running the model over this year's data in multiple times, because what we were trying to investigate here was not just the formation of lakes in 1 year, but how the formation of lakes can influence subsequent years. So here we have in blue is the surface of the Foehn, so the ice shelf surface. Then whenever we get a lake forming, that is in red. And then when it refreezes, you can see here that surface is in green. So this is kind of a weird conceptually to think about because it seems like things are going up in height, but that's essentially a factor of the fact that I'm looking at a 1D model and we think that water is coming in to this 1D area. So I'm assuming I'm modeling in a topographical low and building up water in that. So in that sense, height will be increasing as we're adding things to this area. And we do take account for the fact that this topographical low gets less and less low as we keep piling water into it each year. So if you carry on modeling this, then it kind of flattens out as time goes on. So this shows, first of all, that in the first year, it takes a lot of melting of the Foehn to get any kind of lake, and we get a very small lake in the first year, and again in the second year. But then after that, we get really quite deep lakes, so over 1 meter deep, forming consistently year on year if we run over the model with this warmer data. So what's going on to cause this to happen is that each time these lakes refreeze over, we essentially have a giant ice lens at the near the top of the ice shelf, meaning that lakes in subsequent years are able to form really quite quickly, because to reach an impermeable layer in the ice, all they need to melt through is any new snowfall from year to year. So this shows that transition between the first year and the second year of running this model. So again, 0 is the top of the ice shelf, negative numbers going down, then we've got time going across the x-axis. And the label's been cut off there, but this colour bar is density. So we can see during the winter in Antarctica that the Foehn looks kind of how we'd expect. So we have new fluffy snow at the top, kind of denser Foehn, and then eventually transitioning down into ice as we get further down into the ice shelf. But we can see as we get to the Antarctic summer, sometime in November and December, that melting is happening. And I'm hoping that Zoom is giving you enough resolution that you can see this here. If not, you'll have to believe that there's kind of a triangle here of slightly increased density near the ice shelf surface. So we've got water that has percolated down into the ice shelf surface and has increased the density. It's not become ice yet, but this is water kind of coming down, refreezing, forming those ice lenses and raising the density a bit. Then going on further into the winter, so kind of getting into end of December, January time, we can see that this density then really increases. And I'm guessing you should definitely be able to see this part, which is the bright yellow. And that is where the water is now saturating the ice shelf from the maximum density it can reach right up to the surface and forming a lake. But then as we go on into the Antarctic summer and back into when things start to get colder, this density doesn't go back down because that water's got nowhere to go. It refreezes where it is. And in the next year, we've now got this huge chunk of ice present that is going to mean that lakes in subsequent years form very quickly. We're able to validate this. One example is using Landsat data. So here I showed you before comparing the ice and water pixels to check our catchment area, but also looking at lake depth. So this is some work that Alan Pope did a few years ago, trying to get lake depths from Landsat for the Larsen C ice shelf to check that our lake depths were realistic. And we can see that even though our lakes were kind of towards the larger end, that's unsurprising as I was deliberately simulating the lakes with warm data. But we're definitely kind of within this range that Landsat is observing on the ice shelf. So using this model, it ran some sensitivity tests. Unsurprisingly, the model was most sensitive to air temperature, incoming shortwave radiation, and of course the amount of melt that was coming in from the catchment area. So kind of things that if conditions change on Larsen C, those are going to be the ones that change and potentially cause further melting and deeper lakes. And the effect of the lakes on the surface energy balance was very clear. So if the lakes weren't allowed to form, so we didn't add in that lateral transport of meltwater, and we just had water percolating down into the snow and refreezing, there was 70% less surface melt than if the lakes did form. We also found that the lakes were not too far from a depth where they will not refreeze, so we didn't have to increase, for example, the air temperature too much to get a situation where those lakes definitely didn't refreeze from year to year, even though we don't believe that they are failing to refreeze currently. A huge change isn't needed for that. And thinking about how Larsen C might change into the future, we also had a paper in the Cryosphere a couple of years ago looking at future climate scenarios on Larsen C. So increasing not just the air temperature, which is something that may well change in Larsen C in the future, but also looking at the precipitation, which is also thought to increase. And we can see that increases in both of these lead to lake depths of kind of in the region of sort of 20-ish% increase in lake depths, which can again be quite significant because you then get the extra albedo change and lots more meltwater that can maybe get into crevasses or lead to instability. So we're expecting lakes to maybe remain the whole year in some form, like probably with a frozen lid, but not to completely refreeze over between years in the future in Larsen C if things continue to change the way that they are predicted to. So just a quick summary of that one-dimensional model. It takes the surface energy balance, calculates any heat change through the ice shelf, works out where water is going to go and percolate down into the ice shelf, and then accounts for saturation of the Foehn, subsequent lake formation and refreezing, looking at the lake cycle over multiple years. So this model is open access, the code is out there, quite a few people have used it, which is really exciting. So that's in this James paper here. If anyone does want to use it, then please get in touch. I'm always excited to help people to use this model for whatever their favourite ice shelf is. And I'm currently doing some further studies on Larsen C to compare again with that data from the Midas expedition to look at some of the frozen features that they found on the Larsen C ice shelf. So this was the work of my PhD. Did this great, solve lakes on ice shelves, right? Well, actually no, because ice shelves are not that straightforward. They are unsurprisingly not 1D, and the lakes don't tend to behave and stay still. So for example, we can see here, this is on the Nansen ice shelf. So not only is there a fast flowing river on the ice shelf, taking water to places where it might not necessarily have been melting, so areas of the ice shelf we think that may not have been vulnerable to meltwater induced flexure. But also we have this waterfall feature here as well, which is evacuating water from the ice shelf. So that might actually mean that the water isn't allowed to influence the ice shelf too much because it kind of goes in the river and is removed from the ice shelf before it can potentially damage the ice shelf. And it turns out that Antarctica is covered with all sorts of different weird meltwater features. So here's the Nansen waterfall there, but you can see that there are huge melt ponds and lakes on George VI ice shelf, really long superglacial lake. This one's on Amory, it's like 80 kilometers long, which is crazy. So there are big features, and there are rivers and waterfalls and all sorts of things going on. This one here, sorry, something crazy is now going on with my mouse, just to add some extra fun. Okay, well, that's an image of an ice shelf, lakes on the Amory ice shelf as well. That would have been nice to show you, but I'm not sure what's going on there. All kind of fun of giving virtual talk. So, 1D model isn't actually going to cut it in the real world. So this is why we have been at Georgia Tech developing MONARCHS, which is my terrible acronym that stands for Model of Antarctic Ice Shelf Surface Hydrology and Stability. And the way that MONARCHS works, and the reason that I spent so much time telling you about all the details about this 1D model, is that it takes the 1D model, so we can force this with weather station data or climate model data to account for all those processes that I mentioned. So the surface energy balance, vertical percolation of meltwater, everything that's going on in the vertical direction on the ice shelf. But then we combine lots of these columns to create a 3D grid. So this allows us to move water laterally in a realistic way rather than the kind of fudge that I had to do to create a 1D model. And this allows us to account for processes such as the formation of those rivers, horizontal water routing, accurate lake formation, and other things such as the flexure of ice shelves from the meltwater loading from the weight of those lakes that form. So the idea is that MONARCHS can give us a surface melt distribution for any ice shelf. As long as you have the topography and the input data, then we can tell you what's going on in that ice shelf and where we think the meltwater is going, which is exciting, not just, for example, in planning field expeditions, so from a safety aspect or working out where the water is going to be if you want to investigate that in the field, but also for in the future, because if we can run this with climate model data from the future, we can work out which ice shelves are going to be most vulnerable in the future. Another part of MONARCHS, and I should say this has all been funded as a map proposal, so this is all happening, which is super exciting, is that the information from this can then be put into ice sheet or Earth system models, because they often don't account for these processes in any way at all. There's no kind of ice sheet surface hydrology there at all, or if there is, it's very crude and doesn't allow us to really think about where the meltwater is going and what damage it might be doing to the ice shelf and how it might be causing vulnerability. So in the future, we will be coupling MONARCHS with ISSM, or potentially looking at introducing it as a parameterization into ice sheet or Earth system models, depending on what the needs of those modelling communities are determined to be. So to show you some of the stuff that MONARCHS can do, this first of all is a proof of concept study of the surface routing of meltwater on the ice shelf. So we can see here at the top, this is kind of a hypothetical ice shelf shape. So we have a big topographical low in the centre. So here we have darker reds are higher, whites are lower. So we have this big topographical low, but we also have two kind of smaller lake features in two of the corners of the model. And we start this out with an initial random water distribution. So here, any darker blue is deeper water. And what we would expect here is that any melting that occurs a lot of it would just go straight into that big topographical low in the middle. But we also think that some from kind of these top corners will end up in this smaller lake feature. But then eventually, if that then completely fills up with water, those lakes are going to overtop and more water is going to end up in that topographical low. So running the model with this situation, we can see here, the most useful plot to look at probably here is the final water one. We can see here that not only has most of the water ended up in that low, also it has filled up these two kind of smaller features, and you can actually see where the water has overtopped from these and ended up going down into that larger lake-like feature in the middle. So that was a good proof of concept that this seemed to be working pretty well. So I tested it out on some real ice shelf DEMs. So this, for example, here is from Pine Island Glacier, and good, the GIF is actually working. That's always a worry. We can see here, so on the left-hand side, again, red is height. So this is the Pine Island Glacier DEM. And then if we add a random water distribution to that, we can see how it tends to pool in the areas of topographical lows that can be seen here. You can see that starting to put out some of the meltwater features that have been observed on Pine Island Glacier. Another quick case study that I did earlier this year, I've kind of lost track of time of what year we're in, who hasn't this year, but yeah, I'm pretty sure it was actually in 2020 that there was a huge melt event on George VI ice shelf. Yeah, it was January of this year, so it was noticed first of all in Sentinel imagery, this huge melt event that was happening on George VI. And at first I was kind of not too happy to see this, because I was hoping to collaborate with Ali Banwell and co, who did a great job of going out last year and instrumenting up George VI, and had told me they were going to bring me back lots of lovely data that we could put into MONARCHS. And of course, seeing this, I think they were panicking a little that those instruments might not be doing such a great job, because they could potentially just be floating in a lake everywhere. So keeping everything crossed that we do get some data back from that. But regardless of the data, this did provide quite a nice opportunity to again test MONARCHS and see, since we can see so clearly these features that are forming, how MONARCHS did. So again, we have here a GIF of a random water distribution of seeing where that ended up on George VI. And we can see two main features here. First of all, in red, you can see this kind of horseshoe shaped feature here. That is definitely very topography related, because MONARCHS is picking that up really well. But we can also see that this lake feature here is maybe not being picked up quite so well in the model. It's kind of thinking it's more of a long river than a lake. So that is a suggestion that we should really not just be thinking carefully about what topography we are using, because obviously that highly influences where the meltwater goes, but it's also maybe justification for adding those extra physical processes that I want to put into the model that I will come to in a second. One other thing that the proposal has funded, which I'll mention briefly, so this isn't work that I'll be doing myself, but this is my colleagues Yi Deng and Jingpeng Wang at Georgia Tech, who are looking to add a maximum entropy production model to the ice shelf. And the way that this works is it parameterizes the heat fluxes at the surface, meaning we need fewer input models to be able to correctly work out how much melting is going on at the top of the ice shelf, which for me sounded very exciting, because I know we don't have a ton of weather stations in Antarctica, to say the least. So anything that means we can calculate what's going on there accurately with less data always sounds great. And this is a method that has been tested with Arctic sea ice. So these plots here are from a paper comparing the modelled fluxes to observed sea ice fluxes from the Sheba expedition. We can see that it did a pretty decent job over sea ice, so I'm excited to see the outcomes of this being used over Antarctic land ice. So what is next for the model? Well, I definitely want to think more about river formation, and not just the formation of rivers, but the erosion of the ice by the water flow in those rivers, and how it actually changes the structure of the ice shelf from that ice erosion. I definitely want to look more into lake formation and freeze up, now we can accurately do that in 3 dimensions. And finally, looking at the ice shelf flexure due to water loading, so how that might change where the meltwater ends up and impact on ice shelf future stability. So and I should mention that there are quite a few people who are interested in using this in different areas. So everyone on this slide is either currently using MONARCHS or has applied for, or is in the process of applying for funding to work with it, or has data that I'm directly working with. So it's great that people are interested in it, and people are thinking of adapting it for Greenland too, which is really cool, because there's no good reason why it wouldn't work there. Even though ice shelves are what I care about, all these surface processes obviously are happening on ice that is grounded on land as well. So hopefully there will be lots of great results in the not too distant future coming out from all over Antarctica. Obviously, I'm always more than happy to have more users because there's so many ice shelves to look at, that the more people that want to use this model, then great, because then that kind of takes things off of my to-do list that I don't have to do myself. So please do get in touch if you have a favourite ice shelf that you would like to use MONARCHS to model. So I'm just going to finish up. But instead of first asking for questions, I'm going to give you all some questions. So I want to know, what processes would you like to see incorporated into MONARCHS? What processes do you think are important for the future stability of ice shelves? Or if you're more on the larger scale modelling side, what processes that MONARCHS models do you think would be most useful to incorporate into larger ice sheet or earth system models that aren't currently there? Which ones should we really be focusing on being able to either couple with your models or parameterize for them? And finally, if you have any data we could use to calibrate or validate MONARCHS, the polar regions, there's never going to be enough data, so more is always great. So please do get in touch if you have anything that you think would be useful for us, or if you have some interesting data you want us to try and model to try and understand, then please do get in touch. So with that, I'd like to say thank you very much, and I'm happy to take any questions.
Thank you, Sammy. That was a really neat talk. We have a couple of questions in the chat box. First one I think is from Klaus. Oh, and a couple of hands up I see.
Okay, I'm just going to
I'll start with the chat and then we'll move on to the hands. Klaus, any chance you'd like to read out the question, or are you still with us?
Yeah, okay. I asked, have you considered, or will you do so in the future, the internal stresses in the ice shelf? And related to that, the effects of possible hydrofracturing and the hydrological feedback effects of that hydrofracturing. Now, it's awfully complicated, but that's the question.
Yeah, nothing like starting with an easy question, thank you. No, I have thought about this in a kind of more simple way. So just looking, for example, in that study of how Larsen C might change in the future, I'm looking at if there's going to be enough meltwater produced to even cause crevasse propagation, because you can just do that by checking if they're filled up enough to even cause them to propagate. So I've done it on a simple sense, but we definitely want to be thinking about this more in the future. So there are a couple of ways we can do this. So thinking about where ice shelves are more vulnerable to instability from crevasses being filled with hydrofracture is something that other people have already looked at, and we're hoping to use my model data to compare with their vulnerability estimates to try and work out, to try and get a sense of where things might be unstable in the future. In terms of the internal stresses in the ice shelf, that's something that maybe coupling MONARCHS with larger ice sheet models, for example, might give us more of an insight into. But yeah, that is a hugely complicated area. So definitely something I want to think about more, but that's kind of quite a big step in the future, I think.
Good luck.
Thank you. And then we have a follow-up from Vivian, although I haven't forgotten we have a couple of, we have Julian and Robin.
Well, this is a related question in terms of how will your model relate to the eventually examining the stability of the ice shelf. You know, for example, if there are a lot of meltwater lakes that form on the shelf, because that was suggested as one of the causes of the breakup of Larsen B.
Yeah, sure. So as I said, we're looking to combine the meltwater results with some kind of crevasse stability results to try and learn more about that. But also, I think adding in the ice shelf flexure as well, we can try and get a handle on how important that process is, because that might be something that led to the lake-induced collapse of Larsen B, for example. So yeah, definitely something that I'm planning to look a lot more at in the future, because that's kind of the point of doing this. It's interesting to know where the meltwater is, but if we don't know what it's going to do, then that's the real aim of the study.
Robin, would you like to ask a question?
Sure, thanks. That was a great talk, Sammy. Enjoyed it. I guess my question is something I've been, the more general question of, do you think, this is more speculative, do you think that we're going to see an evolution of the Antarctic ice shelves so they look more like the Greenland ice shelves, in that we lose the firn layer through your sort of densification of the firn process? Do you have a sense of the time scale over which that might happen?
Yeah, this is definitely something that I've been talking to a few people recently about, kind of the Greenlandification of Antarctica. I think it really depends on the ice shelf. I think some areas will go that way much more quickly than others, because, for example, on Larsen C, that firn layer is really deep. So that's going to take hundreds of years for anything to really change there, unless something crazy happens with the temperature. But then other ice shelves that have a very thin or no firn layer, then potentially it won't take very large timescales at all for that to change. So I think it's, yeah, it wouldn't be fair to kind of say the whole continent will become like Greenland, but definitely areas will be looking more like that in the future for sure.
So you'd link it to firn layer thickness, and therefore accumulation rates would be sort of what you would think would be the controlling factor on the role of how fast you can Greenlandify Antarctica.
Yeah, for sure, because where the lakes form in Greenland, that's generally where the firn and snow layer has melted at all completely, so you just have bare ice and lakes. Which is how I'm looking to adapt the model for people who want to use it for Greenland specifically. And that's not really the case so much in ice shelves now, but I mean, if that changes and all that snow is going to melt between seasons, then yeah, that's the way it's going to go.
Great.
Yeah, Julian.
Hi, thank you so much for your talk. I kind of have a connected question to Robin's question. What's the longest that you've run either the 1D model or your new 3D model? And have you thought about kind of seeing how long would it take to run the model to get a density of ice lenses similar to something you see from field studies?
Okay, that is something that I am actually trying to do at the moment. So that I mentioned looking at trying to match some of the field data on Larsen C is something that I've been working on this summer, because there are some really huge ice lenses that have been observed on Larsen C. In terms of running MONARCHS over a longer time period, we haven't done that yet, but it's definitely something that I'm trying to work out a way to parallelize that to be able to do that efficiently. Because even though we have really good competing power at Georgia Tech, that is still kind of
a lot.
Yeah, it's a lot. So yeah, definitely something I want to do. And I've run the 1D model over long time periods, but yeah, working up to be able to do the 3D one, hopefully.
What is long time periods, like 1,000 years or?
No, more like up to 100. I mean, we don't really have, I haven't really looked into realistic forcing data to run it for really long time periods is another thing. So we've kind of just done the 1D model over long time periods just to see what happens if we make things a bit warmer. But to do those studies properly, then really need to use some climate model output, which is one of the plans of things that we were funded to do with MONARCHS. So that will be happening.
Cool, thank you.
I have a question.
Yes, Gary.
Yeah, so we are just beginning to make runs with 1 degree resolution, and it'll probably be 4 or 5 or 10 years in the future we will do 1/2 degree resolution, and then we want to be able to run the model for 100 years. And then we also are mainly interested in what will happen in the future. So to use a model like this, I mean, it needs much coarser resolution. And sort of like things like the river flow on the 1 degree cell is sort of like unimportant and stuff. Be nice if somehow the whole thing could work very nicely, on a 1 degree grid or 1/2 degree grid and stuff like that. A little bit, it seems to be a little bit the model you have. You sort of, if you have what the results, I mean, it's a model that. Sort of after it happens, you can possibly tell us why it happened. But the question is, can you tell us what's going to happen in the future? That's the main thing I'd like to know. And so the question is whether the model can be able to run in a future simulation, which is going to be much coarser resolution and longer timescales, whatever. Okay.
Yeah, so I think to go to those kind of resolutions, like up to a degree, that's a really big difference from what I'm running at the moment, because a lot of the processes that are really important in what's going to happen to ice shelves are much, much smaller scale. So like you said, rivers and the lakes, even the biggest lakes were I think the one I showed was like 80 kilometers is the largest in all of Antarctica. Most of them are much smaller. So I think to be able to think about things on kind of 1 degree of resolution, we'd have to think about parameterizing for that for sure. I'm not quite sure what the best way to do that would be yet, but that's part of our future plans, is to think about the best way and exactly what parts of MONARCHS we need to output to go into a parameterization like that.
Yeah, well, like in general, you know, we have a 1 degree cell has a fraction that's lake and fraction that's ice and ground and stuff like that, whatever. So, you know, but on the other hand, if you have 10 different size lakes and stuff, then it gets a little more complicated and stuff, you know, within the 1 degree cell, I don't know.
Yeah, it definitely does, but that's something we are planning to think a lot more about.
Yeah, okay.
Okay, do we have any other questions?
Oops.
Robin?
Oh, I do have another question. I didn't want to ask two at once, but since I hadn't put my hand down till now, I guess my other question is, did I miss it? And do you have ocean basal melt as part of your ice shelf model? So the fact that we know that the base of the ice shelves are being melted, so that's also changing the morphology. Is that part of your model?
And that's not, I'm only considering the very top of the ice shelf. But that's one of the reasons I want to incorporate it into ISSM, for example, is then we will know how it's interacting with the basal melting as well.
But you could start by putting a, you know, sort of a basal melt, because that's going to influence your flexure, how thick the ice is. So it seems like it might be worth considering how to put it in as before you put it into ISSM.
Yeah, potentially, but also I think at the timescales we're looking at, I don't know if the basal melting would be changing enough kind of between separate years, because we're kind of looking at the flexure kind of between years, whereas I don't know if enough basal melting will be happening that it will really change how much flexure there is, but maybe I'm not right about that. I think that's something I need to talk to Ali more about, because she's the one who definitely.
Well, I think it's more on the question of if you're looking at 100 years evolution.
Yeah.
Then you're going to move these lakes you could possibly move the lakes or the hydrology system from one basal melt regime to another one, right? And then it would matter.
Yeah. Okay. Yeah, that's a good point. That's something I would definitely do.
Right. Right, because if you're worrying about flexure and the whole thing's moving up and down and the thickness is changing, that's going to be a gotcha.
Yes.
Maybe. Who knows? I could be wrong.
We'll see. It's definitely something
okay.
to consider then.
Cool. Thanks.
I think Alex Rebel would like to say.
Hey, Sammy and Robin, I just wanted to add a point, which I think the question about the basal melt, at least in the sort of contemporary or historical simulations, because there is a DEM that is sort of implicit in the 3D model, the DEM naturally includes any basal melt that has occurred, right? If there are differences in the ice thickness due to basal channels, let's say, then that's going to show up in the DEM. So, you know, in places where there is a low due to basal melt, then water should collect in that area. And that's, for example, in the example that Sammy showed from Pine Island, that's exactly what you see, right? You see all these basal channels which are being reflected in the surface topography. And that's where a lot of the water is flowing in those simulations.
Right, and I guess it catches it unless you think that there's, I guess, anyway, it's an interesting thing to think about, whether or not that captures all the basal melt and whether or not the basal melt is constant in each one of your shelves.
Okay, thanks guys. That was a neat little. Do we have any other questions? Okay, doke. Oh, we've got a question from Ron. I should close off soon because we're a bit over. But Ron, do you have a question? Would you like to unmute? Oh. Sorry, I unmuted you, and you unmuted you at the same time, which I didn't think meant that you muted yourself. I muted you. Sorry. Yeah, makes sense. Sorry about that.
Can you hear me?
Yeah.
Okay, excellent. Sorry. So this is a really nice talk, and it seems like a very sophisticated model. This question is related to what Gary was asking about how you would implement something like this in a global Earth system model. You know, we have far less resolution. You know, so for example, as Gary mentioned, you know, maybe, you know, we have 100 kilometers by 100 kilometer grid boxes. You know, possibly we get to 50 by 50, but that's anything smaller, and that's a long way away. So, you know, it seems like in some ways, you know, we don't have nearly enough resolution to simulate some of the processes that you're trying to represent. So I'm wondering, you know, is there ever going to be any overlap? Can we ever introduce something like this into an Earth system model without waiting for the models to catch up to the resolution you need? Or is there maybe a strategy you can take where you don't try to you know, represent all the details, but maybe you look for total lake fraction or other, you know, kind of aggregate quantities? And then do you think there's a way to represent all the processes that seem to be important on sub-grid scale, well, on very small grid scales right now, like, for example, just the redistribution of water from one location to the next? I mean, so I guess I'm asking a question like, first of all, are you optimistic? And second of all, you know, how would you do something like this, or what would you try to reproduce?
Okay, that's a good question, but that's also kind of the question that I asked at the end of my talk, I guess, is what are the processes that I'm simulating that we need to put into Earth system models? Because it's kind of clear that surface melt, it matters, and to really predict future climate, we need to have some kind of representation of this process and of ice shelf vulnerability and collapse in large Earth system models. So yeah, which of those processes are most important? I guess that's something that is still to be determined on my part as I do more case studies of different ice shelves and see how we think they're going to evolve in the future. But that's obviously something, the kind of input that I'm seeking from people who work with Earth system models, that what kind of input can I realistically give you that would be useful on the resolutions that you work on? So yeah, kind of thinking about maybe fractions of ice shelves that are covered by lakes, or kind of giving them a sort of vulnerability number, maybe would be the way forward. But yeah, that's definitely a question that I have as well. It's one that you all have.
Yes, thanks.
Yes, Taz.
Well, I hate to come back to the stresses, but after all, the stability or instability of the ice shelves means breaking up, and that means you need to know the stresses. So the question that I have, what are actually the boundary conditions in terms of stresses that one would have to consider? The wind forces, I mean, the static things, that's the mass distribution between the digital elevation model of the ice shelf, the lake, the water distribution. But you would also need to know actually the underwater negative topography from below. What's the shape at the ice boundary? Then you would need to know probably the wind-driven boundary stresses at the surface and the ocean current stresses. So I mean, we need to know the stresses and the hydrofracture potential related to that. But is that really something we can do with the current level of even data as an input for boundary conditions on the ice shelves?
Yeah, well, the model produces all these stresses. you know, has ocean velocities and air velocities and, you know, atmospheric temperature and stability and things like that.
Yeah, at a much lower resolution. Ron, do you have a question? Nope. I think that was an accident.
Sorry, that was like a residual hand left up. Sorry.
Sorry, I interrupted you, Gary. You were saying that the model produces the stresses that would be required to go into like the higher resolution surface ice model.
Craig, you were asking me a question, or repeating my question, or?
I was just sort of apologizing for interrupting you and seeing if people wanted to carry on that.
No, I was done. I was just mentioning that the model has these stresses and stuff like that. And it is true, what we want to know is how fast the shelf collapses, really. And then from there, we want to go up, you know, up the hill and see how fast the ice comes down.
This is Max here. Great talk, and it was so chock full that it might have gone by and I missed it. But so you have this very detailed model by our standards. What are the prospects of sort of running this sophisticated model and using it to train some, you know, much simpler model that would be more easily applied within our course modeling context? To gauge, you know, certain you know, gross properties of 100-kilometer scales, like fraction of, you know, surface melt ponds for albedo purposes and so on.
Yeah, that's not something I'd really thought about, but it's an interesting idea, because I definitely, like, while it's interesting for me personally as a glaciologist to try and model each kind of individual lake, maybe if just knowing an area has lakes and how much of that area is affected by lakes is a more useful thing to be thinking about in terms of larger models. So that could be a way forward. That's a good thought.
Do we have any final questions? We are slightly over time. Oh, Alex?
Yeah, sorry, I just wanted to add one more thing, which is that about the last question, which is that this is actually something we are thinking about a bit in the group. We've just gotten started in that we have an undergraduate working on this, but there are a lot of interesting ideas from sort of terrestrial hydrology community about how to infer the properties of relatively small scale lakes. So, you know, kilometer scale, which is below the grid resolution of your climate model, from large scale properties. And that's largely because the topography over a large scale range is close to fractal. So we can start to say some very interesting things about, like, you know, what the areal fraction of lake area is on ice shelves, for example. And we're doing this using data from the new ISAT 2 satellite based on, you know, what's going on at the largest scales that might actually be resolved by an Earth system model. So, you know, we're in early days of doing this, but that's definitely something that we're thinking about doing sort of in parallel to this very high fidelity type modeling that Sammy's been leading.
Great, yeah, so it sounds like you're on a good parallel track there. Mm-hmm.
Okie doke. Thank you, Sammy, again very much for a really interesting talk. I hope we hear more from you in the future. Did anyone have any final bits before I close off? Oh, Julian? Julian's clapping. Okay, very good.
I just wanted to give my appreciation for such a great talk.
Appreciate that.
Thanks, everyone. I hope you have a great rest of the day.
Thanks, Craig.
Thank you.